Thank you, Lior. So in stable homotopy, one of the goals is to understand the category of spectrum. So as a first approximation, you should think of spectra as the homotopy coherent abelian group. Now, what do I mean by that? So, okay, an abelian group is, for example, a set A along with the multiplication such that, well, this diagram commutes, where here you swap the two arguments. And a homotopy, a coherent abelian group, well, it should be in particular a space A along with the multiplication such that now this diagram commutes up to like a specified homotopy, along with like a lot of additional data. So given that spectra are like a homotopy enrichment of abelian groups, it's very natural to expect that they would appear in a wide variety of settings in mathematics. And that is indeed the case. So, for example, well, you have like cohomology theories, which have coefficients in abelian groups, but more generally, the so-called extraordinary cohomology theories, well, they have coefficients in spectra. So I'll also be thinking about spectra as cohomology theories. And indeed, the question of like what sort of objects represent cohomology theories is what historically led to the first definitions of spectrum. Now the situation is greatly clarified via an analogy to like classical derived algebra. So you can consider the derived category of the integers, such as chain complexes of abelian groups. Well, this category, it has a symmetric monoidal structure. It has a tensor product, with respect to which the unit is a single copy of z in degree 0. And similarly, the category of spectra, well, it has a tensor product, with respect to which the unit is something called the sphere spectrum. And the derived category of integers, well, it sits inside of spectra, not fully faithfully, which means that we can think of spectra as living over a deeper base than the ring of integers. So one way of making like this notion precise is via something called the chromatic picture of stable homotopy. And okay, here I'm going to fix the prime. And the idea is that if you look at the spectrum of the integers, well, there are 2 points. There's like the generic point, characteristic 0, and then the special point, characteristic b. And then what happens is that, well, over the sphere spectrum, well, the results appear. You mean spectrum? I mean, I'm working over prime spectrum, yeah. So what happens is that over the sphere spectrum, there appear an infinite collection of intermediary primes, which are denoted K1, K2, Kn. And here, this is like K0, and this is K. So over the sphere, there appear like an infinite collection of characteristics which interpolate between classical characteristic 0 and classical characteristic 0. Classical characteristic p. Now, if you think in terms of like cohomology theories, well, the type of cohomology theories which are of height, so this integer is called height. And the type of cohomology theories which are of height 0 include things like rational cohomology. And the things of height infinity of classical characteristic p are things like mod p, singular cohomology. And then some things which live in height 1 are like real or complex K theory. And height 2 has something to do with elliptic cohomology and so on.
Is there a so on? Conjecture.
There's a so on in theory.
Like a non-tautological so on.
So, okay, the idea is that now equipped with these intermediary primes, you can define a collection of localizations and completions of the category of spectra, which behave like open closed decompositions of G's on a space. So again, it's informal definition, but the Kn local category, it roughly consists of spectra which are supported exactly at height n. Now, the chromatic picture of stable homotopy theory, well, like as Asaf mentioned, it originally comes from the algebraic geometry of formal groups. But if you take the analogy with like classical algebra very seriously, then you see you're led to consider like certain structural or categorical properties of the chromatic localizations, which are themselves worthy of independent study. So I want to mention two of those, and this story is roughly due to like Hopkins-Lurie and Kareli-Shlankinovsky and others. And the first I want to mention is higher semiadditivity. So, okay, if you have an ordinary category, which is semiadditive, then the coproducts and the products, they canonically agree. And a consequence is that all the Hom sets, they become like commutative monoids. Or in other words, every object in your category becomes canonically a commutative monoid. So if you are in an infinity category, it's now possible to take limits and colimits over diagrams which are now indexed by spaces. So we say an infinity category is M semiadditive if roughly colimits canonically agree with limits over all M finite spaces A. A space is M finite if its homotopy groups are all finite and vanish above degree n. Now, a consequence is that every object now in such a semiadditive category is canonically a higher commutative monoid. So that means that, okay, so if you think about functions, x-valued functions on A, well, for every A family of points in X, there's a way to sum them to obtain a point in X. And this summation procedure is denoted by the semiadditive integral. And the integral is meant to suggest a whole calculus of integration. Like the semiadditive integral is linear, it satisfies Fubini's theorem, etc., etc. And you should think about it as providing the like user interface that allows you to access the higher commutative monoid structure on the objects of the category.
Question. So in semi-additivity, so like finite products and co-products are the same, but I'm guessing that kernels and co-kernels are not the same.
No, but a space is not category.
Right.
Your limits are along space, it's not along category.
And so
You
wait, so
don't
that's
have error if you just give isomorphic.
okay, because for limit and co-limit, you they're not isomorphic. Okay.
Okay, so now an important example, the important example for us would be the following. Like if say now R is like a commutative ring in a one semiadditive category, well then for every element in R, well you can raise this element to the nth power. So in homotopy theory, when you raise an element in a commutative ring to the nth power, well, it's equipped with an action of sigma n that remembers that you can rearrange the order of all the x's that appear in this product. So you can integrate now over this action, and this produces a natural nth symmetric power operation for every commutative ring in a one semiadditive category. This will be an example to keep in mind. Then the theorem says this is that the chromatic localizations are in fact infinity semiadditive, and this is the finite. Okay, the second thing I want to mention is the Fourier transform. So classically, the Fourier transform is an isomorphism of rings from the group algebra with the ring of functions on the dual. But this actually makes like sense more generally. Anytime you're working over a ring R with roots of unity.
Sorry, just. Sorry, infinity semi-additive. Like infinity finite spaces are finite or what?
Yeah, so infinity semiadditive means you are M semiadditive for every M. So any high finite space, which is a space with finitely many finite homotopy groups, there exists such a common class. Okay, so the Fourier transform, I mean, it really exists more generally anytime you have a ring with roots of unity and a finite of unity group. Then in the Kn local category, well, there is a faithful absolute Galois extension of the unit, which is called En, which we've already heard about. And the Galois group is exactly the same Gn, which exhibits this commutative ring En as something that you should think about it as the algebraic closure of the Kn local sphere.
So is this thing En, is it Kn local or not?
Yes, it is.
So this is like in the Kn local category.
This is in the Kn. Yeah, this is yeah. I got a Galois extension in the Kn local. Okay, so an important example would be that in type 1, G1 is basically P-complete K-theory. And G1 is the units in ZP, and it acts by the Adams operations on topological K-theory. There's a theorem that says that in the K and local categories, there is an invertible Fourier transform which again is an isomorphism between the group algebra and the ring of functions on the dual, where here M is some like sufficiently finite Z module, and this star is like a spectral lift of quantity eigenduality.
If you do it for Z modules, it doesn't have to be spectral, right?
Of what?
If you do it for Z modules, it doesn't have to be spectral. It's like in mod Z.
Right.
Like simpler.
So it
Just a shift of opportunity.
It's a shift.
In the most conventional sense, abelian group.
M?
Yes.
Yes, like a derived abelian. Yeah.
F.
It's like a derived abelian. It's a Z module in spectrum.
And what's the F upper right mod? On mod.
Here, this is some sufficiently finite. Just like, you know.
Finite.
Yeah. Okay, so in light of this, we can make the following definition.
Well, is K of 1, is that like mod PK theory?
Yes.
Yes. Okay, so in light of this,
P completed K theory.
P1 is P complete. Okay, so in light of this, we can make the following definition. say a semiadditive category, an infinity semiadditive category C is called virtually FP orientable. If there exists an invertible Fourier transform after a faithful extension of scalars. Okay, so to give an example, how to think about this virtual FP orientability, and this is okay, I'm sorry, I should have said an invertible Fourier transform for FP numbers. So to give an example of how to think about this, so the category, let's say C is height 0. It is virtually FP orientable when it is additive. So the mapping spaces which are commutative monoids are actually commutative groups. And the reason is because, well, after faithful extension of scalars, there exists an element -1, which is just given by summing along all of the non-trivial primitive p roots of unity. And then it's just multiplication by -1, which gives you the inverse of the map.
So what is in height 0?
So, okay, I didn't say it, but the notion of chromatic height admits a generalization, which is called semi-additive height. So, in general, and
To any, what kind of category?
to a semi-additive, to an M semi-additive category or an infinity semi-additive category. You can ask what is semi-additive height. This is a generalization of chromatic height that agrees with chromatic height on the chromatic localizations.
And in this example, what was the extension of scalars?
In this example, so if it's virtually FP orientable, there exists a faithful extension of scalars under which you have an invertible Fourier transform. And I'm saying that you obtain -1 by summing along the non-trivial primitive p roots of unity.
So what exactly are you, where exactly you're doing the faithful extension of scalars?
So it means that, okay, it means that there exists the commutative algebra in C such that, well, over R, you have an invertible Fourier transform. So when you take like modules over R, the Fourier transform here, there exists Fourier transform in an isomorphism. And additionally, like tensoring with R is conservative, like a faithful extension.
So when R is the unit, mod R is just C.
Yes.
Okay.
Are you saying there is an extension, faithful extension R where you have p roots of unity as a
Yes.
consequence of the existence of Fourier transform?
Yes.
That's
Yes.
the causality.
Okay, so this example suggests that you can think of virtual FP orientability as some higher notion of additivity or infinity semi-additive categories. And then the slogan is roughly that the chromatic localizations are in fact additive of height n. Okay, now we can think about E1, which is again topological K theory. E1 is of height 1. But we can also realize it by taking the algebraic K theory of a ring which is of height 0. And this is the first, perhaps the most basic example of something very general, which is known as the redshift phenomenon. And there are like a variety of qualitative conjectures, now theorems. But the spirit of it is that, well, K-theory increases height. Now, the K-theory of a ring, well, it's obtained in two steps. You first take like modules over R, or say like projective R modules, and then you look at it as a commutative monoid, where the addition is given by the direct sum of modules, and then you take the group completion. And it's in the passage from the ring R to the category of modules over R in which the redshift actually happens. So this suggests that, well, there's actually like a more general like redshift philosophy, which says that, well, categorification, which is the passage from R to modules over R, increases height. So it suggests that you should be able to approach height n+1 phenomena by categorifying height n. Yeah, so okay, in the rest of the talk, I want to explain like what power operations have to do with this.
Can I just ask something stupid? I mean, in theory, like decreases commutativity, right?
Yes.
So is that the same phenomenon that's increasing height?
I don't think it's related. Here I'm working with
different phenomenon.
Yeah, here I'm working with like the infinity ring, so everything is like maximally commutative. When you pass the category of modules, it remains infinite.
But it's also true for E1 rings that the category that you get with the higher height, it's only pointed category, it's not E1. It still increases them.
Okay, so I'll make the following definition. A power operation on commutative algebras in the general symmetric monoidal category is an operation, let's say, which is natural in commutative algebra maps. And this is just a map of sets. It doesn't need to respect addition or multiplication or even have any formulas which prescribe its behavior on addition or multiplication. So the point is that these things are useful. So to convince you, we can make a chart. Say over the rational numbers, there's like not so many of these. You can just take an element x to the nth power. But over fp, say like when p is 2, you have the Steenrod squares. And if you remember the cohomology ring of the space along with its structure as a module of the Steenrod algebra, then you have some hope of saying something about its homotopy type. And then like in K-theory, topological K-theory, you have like the Adams operations. And the mere existence and naturality of the Adams operations on K-theory already gives a very short proof of the Hopf invariant 1 problem. So these are useful. Now, by Yoneda, well, these are exactly natural transformations of the functor phi naught from commutative algebras into sets. And that functor is co-representable. It's co-represented by the free commutative algebra on a single class. So to understand the power operations in a category, you're equivalently asking, what does the free commutative algebra on a single class look like? Okay, so we have the following theorem. Let C be virtually FP orientable of height 1. Then, well, there exists a P derivation for all commutative algebras in C. And a P derivation, it just means it's a natural operation for which the associated lift of Frobenius is the ring homomorphism. So it needs to satisfy some identities that govern its behavior on sums and products. And then additionally, you can actually entirely classify the power operations in C using this operation theta. So again, by this description, I'm interested in pi star of the free commutative algebra on a single class, and this ends up being a polynomial algebra on the class T along with iterates of theta applied to T.
Are you claiming that there's also no relations, or
Yes.
aside from those coming from the p derivation?
Exactly that. Okay, so I want to explain two ways to think about this theorem. So I'll quote a theorem by Bayes, Moeller, Trimble, and it says that if C is a C linear symmetric monoidal, it has a tensor product, and it's additionally idempotent complete category, then you can consider the Grothendieck thing of C, which is just obtained by looking at isomorphism classes of objects with addition given by direct sum, multiplication given by the tensor product. Then this is exactly a lambda ring, which is a ring R with operations from R to R, such that, etc., that satisfy a bunch of conditions. And the idea is that they should be like exterior powers. Now, this characterization is somewhat inexplicit, but there is an alternative characterization due to Joyal, which says that a lambda ring is a ring R along with p derivations for every p that are compatible with each other in some obvious way. And okay, I mean, as an example, this theorem it recovers the theory of Schur functors on, say, representation rings and vector bundles over a space. Then, okay, we can summarize the situation then by saying that, okay, the Grothendieck ring of a C-linear category is a lambda ring. And, well, pi naught of R for R virtually FP orientable of height 1 is, I mean, it's equipped with a single p derivation. So I'm going to think about it as a p typical lambda ring. And this is a clear and concrete instance of the redshift philosophy, because it says, I mean, here it's an example of like a strong redshift hypothesis, which says that everything about semiadditive height 1 is captured in categorification. Okay, I'm going to mention one more result. Okay, if you take the category of finite sets, then okay, its K theory is after P completion, the P complete sphere. This is like it's pretty equivalent classically. And similarly, the K theory of finite C vector spaces is again after P completion, P complete K theory. And there's a map like this exhibiting K theory as an algebra over the P complete sphere, and it actually arises from the homomorphism here, which just takes a set to the finite dimensional vector space on that set. So I'm going to denote it by L for linearization. Now, if G is a finite P group, well, I can take this homomorphism and raise it to the BG. So what happens on pi naught? So this side is the P complete Bernstein ring. This is by Siegel conjecture. And this side is, well, it's the P-complete representation ring. This is like a TS Siegel. And the map is exactly the one that takes a G set to the permutation representation on that G set. Now there's a definition from like finite group theory. Elements in the kernel of this linearization homomorphism from the Burnside ring into the representation ring are called Brouwer relations, and they are of classical interest. Now, okay, the Burnside ring comes from functors from BG into finite sets, and the representation ring comes from functors from BG into finite dimensional vector spaces. Both of those are commutative algebras in a one semi-additive category. So both the Burnside ring and the representation ring, they have semi-additive power operations. In particular, they have these symmetric powers, or these exterior powers, if you like. And you can ask, do these symmetric powers on the Burnside ring give it the structure of a lambda ring? And the answer is no. However, their existence allows you to show the following complete characterization of these Brouwer relations in terms of semi-additivity. So the transformation from the Burnside ring, the natural, if you look at linearization as a natural transformation from the Burnside ring into the representation ring, then it becomes injective upon forcing the Burnside ring to be a lambda ring. So, like, okay, very concretely, it means that there's a diagram like this. Such that, I mean, this map is given by taking the quotient of an ideal, and the elements of this ideal, they can be expressed in terms of relations on power operations, which have to be 0 and a lambda ring. So this gives like a nice semi-additive characterization of Brouwer relations, which, as far as I know, has not been like observed anywhere. Then, okay, to conclude, you can show that now we'll take P to be odd. So in this case, actually, the K1 local sphere is an algebra over the P-complete sphere. And okay, this map here, L, is actually a map of higher one commutative monoids. This is due to Alan Yuan. So you can take this map to the power of BG and now localize the source into Tzadi 1 bar, which I'm using to denote the universal, stable, virtually orientable category of height 1. And okay, well, by this theorem, this becomes a lambda ring, because now this ring is virtually FP orientable. So you can use the semi-additive characterization of Brouwer relations to show that this map on pi naught becomes an isomorphism. So in short, the P-complete sphere is not K1 local, very much not K1 local. But after you force virtual FP orientability, it starts looking a lot like the K1 local sphere. That's it.